Hello everyone, my name is Priya and I am from BSc Chemistry Honors सेकेंड ईयर। आज हम करने वाले हैं हमारा ऑर्गेनिक केमिस्ट्री का फोर्थ चैप्टर जिसका नाम है अल्ट्रावायलेट एब्जॉर्प्शन स्पेक्ट्रोस्कोपी। तो हम इंट्रोडक्शन से शुरुआत करते हैं। One of the important fields of activities of an organic chemist is the determination of structural formula of various substances. In the earlier days, the structure elucidation was mainly based upon the study of classical physical properties and chemical reactions of the compound. The procedure involved was rather laborious and time consuming. However, in the last 50 years or so, some remarkable physical methods have been developed to serve as powerful tools for structure analysis. Of these, the most useful and commonly employed methods are the spectroscopic methods, which are based upon the interaction of electromagnetic radiations with the substance under examination. These methods may further involve the study of ultraviolet, infrared, nuclear magnetic resonance, and mass spectra. Mass spectroscopy is employed to determine the molecular mass and molecular formula of the substance, while UV and IR are used to determine the nature of the functional groups. Finally, the NMR spectroscopy is used to know the complete structure, including the stereochemistry of the substance. The major advantages of employing these spectroscopic methods for structure determination and identification of substances are as follows. They need very little time, and the information obtained is often a permanent record in the form of a chart. The substance is required in very small quantities. The methods are extremely sensitive and highly reliable in stabilizing the structure of compounds and analysis of mixtures of closely related compounds. They can be used for the direction and identification of even very short-lived reaction intermediates. During the spectroscopic studies, the compound is not generally affected chemically and can therefore be recovered unchanged. Continuous analysis is often possible, facilitating the study of reaction rates. In this chapter, we shall deal with the basic aspects of ultraviolet spectroscopy. The electromagnetic spectrum and spectroscopic studies, electromagnetic radiations. Many spectroscopic techniques are based upon the interaction of a compound with the light or some other form of electromagnetic radiations. It is well known that light and other electromagnetic radiations are different forms of energy which have a dual character. They have the properties of both a wave and a particle. They are called electromagnetic radiations because they consist of oscillating electric and magnetic fields which are perpendicular to each other and perpendicular to the direction of motion of the radiations. Some important characteristics of these radiations are the energy of these radiations is inversely proportional to their wavelength or directly proportional to their frequency. These radiations do not require any physical medium and can be transmitted through empty space. For example, light reaches us from the sun through empty space. All types of electromagnetic radiations travel through space with the same velocity, which is nearly 3 into 10 to the power 8 meter per second. Electromagnetic radiations can be described in terms of their characteristics such as wavelength and frequency. Wavelength, it is the distance between two adjacent crests or trough in a particular wave. It is denoted by the symbol lambda. The wavelength is usually expressed in meters, micrometers, nanometers or angstroms. An older term for micrometer is micron and an older term for nanometer is millimicron. Frequency, it is the number of waves which pass across a point in 1 second. It is denoted by the symbol V. The frequency is generally expressed in cycles per second or simply second inverse or hertz. The frequency and wavelength are related to each other as V is equals to C by lambda. Wave number, it is the reciprocal of wavelength and represents the number of wave per centimeter. It is denoted by the symbol V bar. Wave number is generally expressed in centimeter inverse. Wave number is related to wavelength and frequency as V bar is equals to 1 by lambda is equals to V by C, where C is the velocity of radiations in centimeter. In SI system, the unit of wave number is meter inverse. Energy of electromagnetic radiations. Electromagnetic radiations are associated with discrete energy units called quanta or photons. The energy of a photon is directly proportional to its frequency or inversely proportional to its wavelength as shown by the following equation. E is equals to h mu is equals to hc by lambda. Electromagnetic spectrum. Visible light, which can be detected by the human eye, constitutes only a very small part of electromagnetic radiations. The full range of these radiations is indeed very large, and their wavelengths vary from a very small fraction of a meter to many kilometers. The arrangement of entire range of electromagnetic radiations in increasing order of their wavelengths or decreasing order of their frequencies is known as electromagnetic spectrum. The complete electromagnetic spectrum, along with common names used to identify different ranges of wavelengths. Of the complete electromagnetic spectrum, spectroscopic techniques are concerned primarily with radio frequency radiations, infrared radiations, and ultraviolet visible radiations. Principle of absorption spectroscopy. It is interesting to note that particularly all the important spectroscopic methods used for structural analysis belong to the field of absorption spectroscopy, which studies the absorption of electromagnetic in relationship to molar structure. When a beam of electromagnetic radiation is passed through a substance, the radiation may be either absorbed or transmitted depending upon the wavelength of the radiation and molecular structure of the substance. Absorption of radiation would naturally bring about an increase in the energy of the molecule, the energy gain being directly proportional to the frequency or inversely proportional to the wavelength of radiation. The increase in energy of a molecule may lead to electronic excitation, whereby electrons are raised to higher energy levels. Alternatively, it may bring about an increase only in the vibrational or rotational energy of the molecule. Electronic excitation can be caused by only high energy radiations such as ultraviolet and visible radiations. On the other hand, vibrational and rotational energy levels can be raised even by relatively low energy infrared radiations. A very important condition for a molecule to absorb electromagnetic radiation is that the energy of a photon of the radiation must be equal to the energy difference between two vibrational or rotational or electronic energy states of the molecule. In other words, the particular wavelength of radiation that a given molecule can be absorbed is determined by changes in vibrational or rotational or electronic states that are permitted to a molecule of that structure. The absorption of radiation is observed instrumentally by passage of radiation through a sample of substance and automatic analysis of the intensity of transmitted light radiations. A record of the amount of radiation absorbed or transmitted by a given sample as a function of wavelength of radiation is called absorption spectrum. One might expect an absorption spectrum to consist of a series of lines, but actually the spectrum is made of absorption bands with peaks of maximum intensity. The instrument used for recording a spectrum is known as spectrophotometer or spectrometer. Having discussed the principle of spectroscopy, we proceed further to discuss ultraviolet spectroscopy in some detail. Ultraviolet spectroscopy. Ultraviolet spectroscopy involves the measurement of absorption of light in the visible and ultraviolet regions by the substance under investigation. Since the absorption of light involves the transition from one electronic energy level to another within a molecule, UV spectroscopy is also known as electronic spectroscopy. It will be quite appropriate at the stage to study the laws of which govern the absorption of light. The absorption laws. There are two laws which express respectively the relationship between absorption of light by a substance and its molar concentration and the length of the path through which the light passes. These are Beer's law. According to this law, when a beam of monochromatic light is passed through a substance dispersed in a non-absorbing solvent, the absorption of light is directly proportional to the molar concentration of the absorbing substance. Lambert's law. This law states that when a beam of monochromatic light is passed through a substance, the absorption of light is directly proportional to the path length of the sample of the substance. Beer-Lambert's law. The two laws stated above can be combined to get a general absorption law termed as Beer-Lambert's law. It may be stated as the absorption of light by a substance at a particular wavelength is proportional to the number of molecules of the substance in the path of light. Mathematically, Beer-Lambert's law may be expressed as log of I naught upon I is equals to E dot C dot L. I naught is intensity of incident light, I is intensity of transmitted light, C is concentration of the absorbing substance in mole liter inverse, L is path length or thickness in centimeter of the cell containing the sample, E is proportionality constant known as molar absorptivity. The expression log of I naught upon I is termed optical density or absorbance. It is a measure of absorption of radiation by a sample. Therefore, Beer-Lambert's law may also be expressed mathematically as A is equals to log of I naught upon I is equals to epsilon A dot A C dot L. Limitations of Beer-Lambert's law. Beer-Lambert's law is strictly obeyed when dealing with the UV spectra of single species. However, if a sample contains different structural forms of the molecules in equilibrium with each other, such as in case of keto-enoltottomers, this law is not obeyed. It is also not applicable if the solute sample and solvent interact with each other to form complexes. Molar absorptivity. It is a proportionality constant which relates the observed absorbance at a particular wavelength to the molar concentration of the absorbing substance and the length of the path of light in centimeter. It may be expressed as epsilon is equals to log of I naught upon I upon Cl is equals to A upon Cl. Molar absorptivity is a measure of the intensity of absorption at a particular wavelength and has the dimensions of centimeter square mole inverse, but these units are seldom used. It is a characteristic property of a compound and is not affected by its concentration or the length of path of light. Its value ranges from 0 to 10 to the power 6. Values above 10 to the power 4 constitute high intensity absorptions, while values below 10 to the power 4 are low intensity absorptions. Present transmission. Since I naught upon I is the ratio of intensity of incident light to the transmitted light, the transmittance of a sample will be naturally given by the relation T is equals to I upon I naught. Present transmittance is equals to 100 into I upon I naught. Now, mechanics of recording the UV spectrum, presentation of the spectrum. Excellent ultraviolet spectrophotometers are now available which can conventionally record the spectra over the range 200 to 800 nanometer. Since oxygen of the atmosphere strongly absorbs light at about 200 nanometer and below, the use of wavelengths shorter than 200 nanometer is not applicable unless special vacuum techniques are employed. The ultraviolet spectra are always recorded on a wavelength scale in millimicrons or nanometers. Procedure for recording the ultraviolet spectrum. The given compound is generally dissolved in some suitable solvent which does not itself absorb light in the region under examination. The commonly employed solvents are 95% ethanol, hexane, and water. The solution of the compound is placed in a suitable transparent container which does not absorb light in the region being studied. Generally, a quartz cell of 1 centimeter path length is used for this purpose. At the same time, some solvent is taken separately in another quartz cell which serves as a reference cell. The sample solution and the solvent are then exposed to the ultraviolet and visible radiations in a spectrophotometer in which a hydrogen discharge lamp is usually employed as a source of light in the ultraviolet region, while a tungsten filament lamp is used for the visible region of the radiation. The spectrometer operates by comparing the amount of light in the beam transmitted through the sample with the reference beam which passes through the reference cell. This compensates for any absorption of light by the cell and the solvent. In this way, the spectrometer measures the amount of light absorbed by the compound at each wavelength of the ultraviolet and visible region. This absorption gets recorded on a chart part as a plot of wavelength of the entire region versus the absorbance of light at each wavelength. The spectrum obtained consists of a small number of broad peaks, quite often only one peak is seen. UV spectrometer. A simplified diagram of UV visible spectrometer is shown in figure 4.2. It consists of the following parts. A source of radiations which emits all wavelength of UV radiations. The commonly used source of light in the UV region is the hydrogen or deuterium discharge lamp, which a tungsten filament lamp is used for producing visible light. Second, a monochromator which splits the radiations into individual wavelengths. The single wavelength of radiation is split into two beams, one of which passes through the sample cell while the other passes through the reference cell. A detector which continuously measures the intensity ratio of the beams transmitted through the sample and the solvent respectively. A recorder chart paper which automatically records the absorption of light at each wavelength has a graph of absorptions versus wavelength. Presentation of the spectrum. The ultraviolet spectrum of 1,3-butadiene in hexane is shown in figure 4.3. It may be seen that absorption of ultraviolet radiations by 1,3-butadiene begins at wavelength below 200 nanometer and continues up to about 260 nanometer. This is the figure. The spectrum is reported as a single absorption peak using the notation lambda maximum is 217 nanometer. In reporting the UV spectrum for analytical purposes, the molar absorptivity epsilon at the wavelength of maximum absorption is also quoted along with lambda maximum. For example, the molar absorptivity of 1,3-butadiene at lambda maximum is 217 is 20,900. Therefore, the UV spectrum is reported as 1,3-butadiene lambda maximum is equals to 217 nanometer. Sometimes the ultraviolet absorption curves are also presented by plotting a molar absorptivity against the wavelength. For example, the ultraviolet spectrum of acetone in hexane is shown below in figure 4.3. This is the figure. Since the UV spectra generally shows broad peaks and valleys, the actual spectra are rarely used. The spectral information is given by listing the value or values of lambda maximum along with the molar absorptivity for each value of lambda maximum. Principle of UV spectroscopy. Absorption of visible and ultraviolet light produces change in electronic states of molecules associated with the excitation of an electron from a lower to a higher energy level, but it must be noted that each electronic level in a molecule is associated with a number of vibrational sublevels, and each vibrational level in turn is associated with a number of rotational sublevels. Therefore, in its transition to higher energy level, an electron can go from any of the sublevels corresponding to various vibrational and rotational states in the ground state to any of the sublevels in excited state. Appreciance of broad bands and not sharp peaks in the spectrum. If the electronic excitation in the molecule had occurred without any accompanying changes in vibrational and rotational sublevels, the spectrum would have consisted of sharp lines with each line representing a change in electronic state. But due to the mixing of vibrational and rotational changes with electronic changes in the molecule, there will be a large number of possible transitions requiring only slightly different energies. This will require the absorption of a large number of wavelengths which are very close to each other. As a result, the absorption spectrum contains a large number of lines which are too close together to be distinguished separately and are recorded in the form of broad bands in the spectrum obtained. As stated earlier, the spectrum is described in terms of the position of the top of hump and the molar absorptivity. Electronic excitations. Electronic transition involves the promotion of an electron from one orbital to another orbital of higher energy. In a molecule, the electron promoted may be a sigma electron and a pi electron, n electron, as illustrated with the help of electron pairs in formaldehyde as shown on the right hand side. The higher energy orbitals are antibonding molecular orbitals which may be vacant in the ground state of the molecule. The antibonding orbitals associated with the sigma bond is called the sigma star orbital, and that associated with pi bond is called the pi star. Not concerned orbital. Since the n electrons are not concerned in both formation, there are no antibonding orbitals associated with them. The electronic transitions taking place in the ultraviolet and visible regions are of the following types. A brief account of the various types of electronic transitions is as follows. Sigma is sigma star transitions. Transitions in which a sigma bonding electron is excited to an anti-bonding sigma star orbital are called sigma to sigma star transitions. These transitions can be shown only by compounds such as saturated hydrocarbons in which all valence shell electrons are involved in the formation of sigma bonds. The energy required for these transitions is very high and consequently these occur at very short wavelengths. For example, in methane, the absorption of energy for such transitions occur at only 125 nanometer. Since these wavelengths are lesser than 200 nanometer and fall in the vacuum UV region, the usual spectroscopic technique cannot be used in case of such transitions. N to sigma star transitions. These are the electronic excitations from a non-bonding atomic orbital to an anti-bonding sigma star orbital. Compounds having non-bonding electrons on heteroatoms such as oxygen, nitrogen, sulfur or halogens can show N to sigma star transitions. These transitions are of lower energy and hence occur at longer wavelength than sigma to sigma star transitions. The energy required for these transitions decreases with the decrease in the electronegativity of the hetero compound, and therefore the wavelength of absorption increases. For example, methyl chloride absorbs at 174 nanometer while in methyl iodide absorption takes place at 258 nanometer. Similarly, amines absorb at higher wavelength than alcohols as nitrogen has lesser electronegativity than oxygen. These observations can be attributed to the fact that greater the electronegativity of the heteroatom, more firmly the non-bonding electrons are held by it. Therefore, more energy is required for N to sigma star transition. Hydrogen bonding of the compound with the solvent also shifts the absorption to shorter wavelength, but in general, N to sigma star transitions are not much importance. N to sigma pi star transitions. These are the transitions in which an electron in a non-bonding atomic orbital is promoted to an anti-bonding pi star orbital. Compounds having double bonds between heteroatoms show these transitions which appear as weak absorption bands. These transitions require only small amounts of energy and takes place within the range of ordinary ultraviolet spectrometer. However, the intensity of the absorption is generally very low. For example, the carbonyl group of saturated aldehydes or ketones exhibits an absorption of low intensity at about 285 nanometer. Pi to pi star transitions. The transition in which a pi electron is excited to an antibonding pi star orbital is called pi to pi star transitions. These have relatively higher energy requirement than N to pi star transitions, and absorption generally takes place outside the ordinary ultraviolet region for simple molecules containing isolated unsaturated centers, but the intensity of absorption is very high. For example, the pi to pi star transition for simple aldehydes or ketones produces an absorption band of high intensity at about 180 nanometer. For a simple alkene like ethylene, such as transition takes place in still for far ultraviolet region. Effect of conjugation. Conjugation of double bonds lowers the energy required for the electronic transition. As a result, molecules containing conjugated systems such as greater than carbon double bond carbon absorb the radiations of longer wavelength than in case of non-conjugated systems, and absorption bands appear in the ordinary ultraviolet range. For instance, 1,3-butadiene shows lambda maximum 270 nanometer in contrast to ethylene which shows lambda maximum 175 nanometer. To understand the effect of conjugation on lambda maximum, let us start with ethylene, which is the simplest unconjugated alkene. The double bond in ethylene consists of a sigma bond formed by the combination of sp2 hybrid orbitals of two carbon atoms and a pi bond formed by the combination of unhybridized 2p orbitals. Due to the large difference in the energies of pi bonding and pi antibonding molecular orbitals, a pi to pi star transition takes place with the absorption of radiation below 200 nanometer. Therefore, these transitions occur only in far ultraviolet regions. In a conjugated system such as 1,3-butadiene, there are two ethylene units in conjugation with each other. Due to conjugation, the pi bonding orbitals of the two ethylene units interact with each other to form two new bonding orbitals, pi 1 and pi 2 of different energies. Similarly, there is formation of two pi star orbitals, pi star 3 and pi star 4 of different energies from the two ethylene units. The energy difference between highest occupied pi molecular orbital and the lowest unoccupied molecular orbital for 1,3-butadiene is less than it is for ethylene. Energy gap becomes smaller. The position of energy absorption moves to longer wavelength which falls within the ordinary ultraviolet region. With the increase in the number of double bonds in conjugation, the energy difference between HOMO and LUMO further decreases, so that absorption moves to still longer wavelengths. The spectrum of 1357 octatetrene in hexane exhibits lambda maximum 290 nanometer. If there are enough double bonds in conjugation, absorption will ultimately move into the visible region and the compound will be colored. For example, beta carotene, a naturally occurring yellow pigment containing 11 double bonds in conjugation, owes its color to absorption in the visible part of light. Another effect of conjugation is that With the increase in conjugation, the number of possible UV transitions increases and the spectrum becomes more complex. To sum up the above discussion on electronic transitions, it may be stated that the organic chemist is primarily interested in two types of transitions, particularly in conjugated system. These are N to pi star and pi to pi star. It may be noted that transitions to antibonding pi star orbitals are associated only with unsaturated centers in the molecules. Transition probability. It is interesting to note that it is not necessary that exposure of a compound to ultraviolet or visible light must always lead to an electronic transition. On the other hand, the probability of a particular electronic transition depends upon the value of molar absorptivity and certain other factors. Accordingly, transitions have been divided into two categories: allowed transitions and forbidden transitions. Allowed transitions. These are transitions which have epsilon maximum 10 to the power 4 or more and the probability of their occurrence is very high. These are generally due to pi to pi star transition. For example, pi to pi star transition in 1,3 beta diene, which shows absorption at 270 nanometer and has epsilon maximum 20,900, represents an allowed transition. The pi and pi star orbitals involved in these transitions lie in the same plane and can undergo overlapping to a large extent in the excited state. Therefore, pi to pi star transitions are highly probable. Forbidden transitions. These are transitions for which epsilon maximum is generally less than 10 to the power 4. These are usually related to n to pi star transition. For example, n to pi star transition of a saturated aldehyde or ketone showing weak absorption near 290 nanometer and having epsilon maximum less than 100 is a forbidden transition. It should be clearly understood that forbidden transition does not mean that such a transition cannot take place at all. It just tells us that the probability of the transition is very low. To clarify this statement, let us consider the n to pi star transition. The orbital containing the non-bonding electrons, regions in space belonging to these orbitals can overlap only to a very small extent. As a result, the probability of excitation of n electrons to pi star orbitals is very low. Concept of chromophore and auxochromes. Chromophore. The term chromophore was originally used to denote a functional group or some other structural feature, the presence of which imparts a color to a compound. For example, nitro group is a chromophore since its presence in a compound imparts yellow color to the compound, but these days the term chromophore is used in a much broader sense. It is now defined as any group which exhibits absorption of electromagnetic radiations in the visible or ultraviolet region. It may or may not impart any color to the compound. List some simple chromophore groups along with their lambda maximum and epsilon maximum and the type of transition involved. Now, it may be seen that chromophores are of two types. Chromophores such as greater than carbon-carbon double bond and less than and carbon-carbon triple bond, which contains pi electrons and undergo the pi star transitions. Chromophores such as greater than carbon double bond oxygen, nitrogen double bond nitrogen, and NO2, which contain both pi and n electrons, they can undergo pi to pi star as well as n to pi star transitions. Two compounds having the same chromophoric group generally exhibit absorption at nearly the same wavelength lambda maximum and have nearly the same molar absorptivity. Therefore, it should be possible to identify the presence of a particular functional group in an unknown compound by the comparison of its UV spectrum with the data of already known compounds. But the position of absorption maximum and the intensity of absorption can be modified by a number of factors discussed below. Auxochrome. An auxochrome is a group which itself does not act as a chromophore, but when attached to a chromophore, it shifts the absorption maximum towards longer wavelength along with an increase in the intensity of absorption. Some commonly known auxochromic groups are minus OH, minus NH2, OR, NHR, and NR2. All auxochromes contain one or more non-bonding pair of electrons. When an auxochrome is attached to a chromophore, it leads to conjugation or helps in extending conjugation by sharing of its non-bonding pair of electrons as shown below. Due to conjugation, there is a decrease in the energy difference between the ground state and excited state of the group. As a result, the absorption shifts to longer wavelength. At the same time, there is an increase in the intensity of absorption. For example, when the oxochrome NH2 group is attached to benzene ring, it increases lambda maximum as well as epsilon maximum as given below. NH2 acts as a oxochrome by extending the conjugation in benzene by the participation of a non-bonding pair of electrons in conjugation. Similarly, ethoxy group acts as an oxochrome as shown below. Change in position and intensity of absorption. For isolated chromophore groups such as carbon-carbon double bond and carbon-carbon triple bond, absorption occurs in far ultraviolet region which cannot be easily studied. But the position of absorption maximum and the intensity of absorption can be modified in different ways by some structural changes or change of solvent. These changes can produce four kinds of effects: bathochromic effect or redshift, hyposochromic effect or blue shift, hyperchromic effect, hypochromic effect. These effects are discussed below. Bathochromic shift or red shift, it involves the shift of absorption maximum towards longer wavelength. It can be brought about by three different methods as given below. By attachment of an oxochrome to the chromophore. When an oxochrome such as OH and NH2 is attached to a chromophore, it leads to conjugation or helps in extending conjugation. As a result, absorption shifts to longer wavelength. For example, when the ensochrome NH2 group is attached to benzene ring, it shifts the absorption band from 255 nanometer to 280 nanometer by conjugation of two or more chromophoric groups. Bathochromic shifts is also produced if two or more chromophores are present in conjugation in a molecule. For example, as already studied, ethylene shows pi to pi star transition at 170 nanometer while 1,3-butadiene, where two double bonds are in conjugation, shows lambda maximum at 217 nanometer. By using solvent of lower polarity, it is also possible to achieve bathochromic shifts by using solvent of lower polarity. For example, use of a solvent of lower polarity produces a red shift in the N2 pi star absorption of carbonyl compounds. Acetone shows lambda maximum at 264 nanometer in H2O, but it shifts to 279 nanometer when hexane is used as solvent. Hyposochromic shift or blue shift, it involves the shift of absorption maximum towards shorter wavelength. It may be brought about as follows: by removal of conjugation in a system. For example, protonation of aniline causes a blue shift from 280 nanometer to 203 nanometer. This is because anilinium ion thus formed has no lone pair of electrons on nitrogen which can conjugate with benzene ring. By using solvent of higher polarity, use of solvent of higher polarity can also bring about hyposochromic shift. For example, use of a solvent of higher polarity case is a blue shift in the N to pi star absorption of acetone. Hyposochromic effect. This effect involves an increase in the intensity of absorption. It is usually brought about by introduction of an oxochrome. For example, introduction of methyl group in position brought about by introduction of an oxochrome. For example, introduction of methyl group in position 2 of pyridine increases lambda maximum from 2750 to 35604 pi to pi star transition. Hyposochromic effect, it involves a decrease in the intensity of absorption. It is brought about by groups which distort the geometry of the molecule. For example, when a methyl group is introduced in position 2 of a biphenyl, hypochromic effects take place due to distortion caused by methyl group. As a result, lambda maximum decreases from 19,000 to 10,250. It may noted that a bathochromic shift is generally accompanied by a hyperchromic effect, while hyposochromic shift is accompanied by hypochromic effects. The various kinds of absorption and intensity shifts have been summed up. Solvent effects and choice of solvent. Solvent effects. The solvent used for dissolving a compound under examination has a profound effect on the UV spectrum of the compound as given below. Effect on fine structure. As a result of interactions of solute with solvent molecule, the fine structure of the absorption bands is blurred out and a smooth curve is obtained. This smooth out of the spectrum deprives us of much useful information about complex molecules. The smoothing out effect is more in polar solvents than in non-polar solvents. The fine structure of UV spectrum is best observed in vapor phase. This is the diagram. Effect on the position and intensity of absorption maximum. Changing the polarity of the solvent may also lead to change in the position and intensity of absorption maximum. Effect on non-polar compounds. In general, changes in polarity of the solvent do not cause any significant shift in the spectra of non-polar compounds such as and conjugated hydrocarbons. For example, the absorption maximum for non-molar compounds in practically the same in alcohol as well as in hexane. Effect on polar compounds. In case of polar compounds such as alpha beta unsaturated carbonyl compounds, the absorption maximum generally gets shifted with the change in the polarity of solvents. It has been observed that such shifts are of two types. Shift in N to pi star transitions. Increase in the polarity of the solvent shift N to pi star transition to shorter wavelength. For example, absorption maximum of acetone is at 279 nanometer in hexane, at 270 nanometer in ethanol, and at 264 nanometer in water. This shift towards the shorter wavelength is mainly due to the greater stabilization of the ground state than the excited state through dipole-dipole interaction, formation of hydrogen bonds or solvation with the polar solvent. As a result, the difference in energy between the ground state and the excited state increases and the absorption shifts towards shorter wavelength. Let us, for example, consider the blue shift of the N to pi star carbonyl absorption. The carbonyl group is more polar in the ground state than in the excited state. Therefore, the extent of hydrogen bonding between the ground state and the polar solvent like water and alcohol is much more than between the excited state and the solvent. In other words, ground state is stabilized to a greater extent and undergoes greater lowering of energy than the excited state. Consequently, the energy difference between the two states increases and the absorption shifts towards the shorter wavelength. Shifts in pi to pi star transition. Increase in the polarity of the solvent shifts pi to pi star transitions to longer wavelength. For example, it has been observed that as compared to solution in hexane, solution in ethanol generally shows a red shift of about 10 to 20 nanometer. The shift of pi to pi star absorption towards longer wavelength is largely due to the greater stabilization of excited state relative to ground state through dipole-dipole interaction of or solvation. As a result, the energy difference between the ground state and the excited state decreases and the absorption shifts towards larger wavelength. For example, the molecule of ethylene is more polar in the excited state than the ground state due to the greater polarity of pi star orbital compared to pi orbital. As a result, the pi star molecular orbital will be relatively more stabilized by dipole-dipole interaction with the polar solvent as compared to stabilization of the ground state. Therefore, lesser energy will be required for such a transition and the absorption will shift towards larger wavelength. Shifts in N to sigma star transitions. N to sigma star transitions are very sensitive to hydrogen bonding. For example, alcohols and amines from hydrogen bonding with the solvent molecules due to the presence of non-bonding electrons on the heteroatom. As a result, more energy is required for N to sigma star transition in polar solvents and shifts towards longer wavelength take place. To sum up, if a group is more polar in the ground state than in the excited state, increasing the polarity of the solvent shifts the absorption to shorter wavelength. If a group is more polar in the excited state than in the ground state, increasing the polarity of the solvent shifts the absorption to longer wavelength. Choice of solvent. A suitable solvent for ultraviolet spectroscopy should meet the following requirements. It should be transparent in the wavelength region under examination. It should not itself absorb radiations in the region being examined. It should be less polar so that it has minimum interaction with the solute molecules and has no effect on the fine structure of absorption bands and the position of absorption bands. The most commonly employed solvent is 95% ethanol. It is cheap, has good dissolving power, and does not absorb radiations about 210 nanometer. In other words, it is transparent about 210 nanometer. Commercial ethanol should not be used as it contains some benzene which undergoes absorption in the UV range at about 280. Some other solvents which are transparent above 210 nanometer are N-hexane, cyclohexane, methanol, water and ether. Hexane and other hydrocarbons are sometimes preferred to polar solvents because they have minimum interactions with the solute molecules. Benzene, chloroform and carbon tetrachloride cannot be used because they absorb in the range of about 240 to 280 nanometer. Some characteristic absorption bands. Table 4.2 lists the wavelengths of maximum absorption of corresponding molar absorptivities or extinction coefficients for some typical ultraviolet bands of simple molecules containing different groups. So this is the table which shows extended coefficients. The vapor state refers to the use of compound in the neat form. These are the examples. Now Woodward-Fisher rules for calculating absorption maxima. By studying the ultraviolet absorption spectra of a large number of compounds, Woodward deduced certain rules for corresponding lambda maximum with molecular structure. Since then, these rules have been modified by Scott and Fisher as a result of more experimental data. The modified rules known as Woodward-Fisher rules enable us to calculate the position of lambda maximum for a given structure by relating the position of lambda maximum with the position and degree of substitution of chromophore. The calculated values are generally within 2 or 3 nanometer of the experimental values. We will now consider these rules briefly for different classes of compounds. Woodward-Fisher rules for calculating lambda maximum in conjugated dienes, trienes and polyenes. Before we consider the rules for dienes, trienes, etc., it will be useful to explain some terms involved in discussing the rules. Homoannular diene. It is a cyclic diene which contains conjugated double bonds in the same ring. Heteroannular diene. It is a cyclic diene in which double bonds in conjugation are present in different rings. Endocyclic double bond. It is a double bond present in a ring. Exocyclic double bond. It is a double bond in which one of the doubly bonded atoms is a part of ring system as shown above. Woodward-Fisher rules for conjugated dienes, trienes, polyenes. According to these rules, each type of diene or triene system has a certain fixed value at which absorption takes place. This constitutes the basic value or parent value. The contributions made by various alkyl substituents or ring residues, double bonds extending conjugation and polar groups such as chlorine, bromine, OR are added to the basic values to get lambda maximum for a particular compound. The parent values and contributions of different substituents groups are given in table 4.3. Now we will see that these are some examples and problems to solve related to this topic. Now, Woodward-Fisher rules for alpha-beta unsaturated carbonyl compounds. Woodward-Fisher rules for calculating lambda maximum for alpha-beta unsaturated carbonyl compounds modified by Scott may be summed up as given below. Parent values alpha-beta unsaturated or 6-membered ring ketone 215 nanometer, alpha-beta unsaturated 5-membered ring ketone 202 nanometer, alpha-beta unsaturated aldehyde 207 nanometer. Increments each alkyl substituent or ring residue at alpha position 10 nanometer, beta position 12 nanometer, gamma and higher positions 18 nanometer. Each exocyclic double bond 5 nanometer, double bond exocyclic to 2 rings simultaneously 10 nanometer, double bond extending conjugation 30 nanometer, homoannular conjugated die in 39 nanometer. In these compounds, the actual spectra obtained are affected considerably by the nature of the solvent employed. Therefore, a solvent correction is applied to this calculated value to obtain the value for that particular solvent. However, we are not discussing the solvent corrections at this stage. A few examples are given below for the sake of illustration of above rules. These are the examples which with solution. Let us now discuss ultraviolet spectra of conjugated enes and enones. Okay, it has already been studied that the presence of conjugated systems in a molecule plays a very important role in ultraviolet spectroscopy. If a molecule contains two chromophoric groups separated from each other by two or more single bonds, their effect on the UV spectrum of the molecule is generally additive. But if the two chromophoric groups are conjugated, they are practically equivalent to a new chromophore and a markedly different spectrum is obtained. To illustrate this statement, we now consider the ultraviolet spectra of conjugated enes and enones. Ultraviolet spectra of conjugated enes. The UV spectra of all enes, whether conjugated or non-conjugated, involve the pi to pi star transitions. Still, the spectra of conjugated enes are markedly different from non-conjugated enes. This is basically due to the fact that in conjugated enes, the energies of pi to pi star orbitals are much closer together than in simple enes. As a result, the conjugated system requires lesser excitation energy as compared to non-conjugated system, and therefore the absorption shifts to longer wavelength. All acyclic conjugated dienes exhibit a redshift of about 40 nanometer with respect to unconjugated enes, giving intense signal in the region 215 to 230 nanometer. Extending conjugation gives rise to additional redshift along with increase in intensity. Lambda maximum values of the following polyenes clearly illustrate the effect of conjugation and its extent on lambda maximum of conjugated enes. Okay. It may be seen that there is a broad absorption band in the region between 210 nanometer and 260 nanometer, and the absorption is maximum at 245 nanometer. 242 nanometer. Ultraviolet spectra of conjugated enones. Conjugated enones exhibit strong absorption in the region 215 to 250 nanometer due to pi to pi star transition, and weak absorption in the 310 to 330 nanometer range due to n to pi star transition. As compared to unconjugated ketones, there is a red shift in both the types of absorption due to conjugation. It may be noted that the weak n to pi star bands is sometimes not observed at all because it is masked by the very intense band. Now this is the graph. Interperfection of ultraviolet spectra. Applications of ultraviolet spectroscopy. The interpretation of ultraviolet spectra of unknown compounds can be very useful in deriving structural information about the compounds. The main application of ultraviolet spectroscopy are as follows. Detection of conjugation. Ultraviolet spectrum helps to show whether a given compound contains certain groups in conjugation with each other or not. The conjugation may be between two or more carbon-carbon double bonds, between carbon-carbon and carbon-oxygen double bonds, or between double bonds and an aromatic ring. UV spectrum can also reveal the presence of an aromatic ring itself, and the number and locations of substituents attached to the carbon of the conjugated system. Since 4-methyl pent 3-ene has the carbon-carbon double bond and the carbonyl group in conjugation with each other, both pi to pi star and n to pi star absorption bands in it will be at longer wavelength than in 4-methyl pent 4-ene, in which there is no conjugation. Thus, UV spectrum enables us to determine whether a compound contains a conjugated system or not. Extent of conjugation. UV spectroscopy is also employed to estimate the extent of conjugation in polyenes. With the increase in the number of double bonds, the absorption shifts to longer wavelength. For compounds having 8 or more double bonds, the absorption may shift to even visible region of light. Thus by determining the lambda maximum of a given polyene, it may be possible to know the number of double bonds in conjugation. Determination of configuration of geometrical isomers. In case of geometrical isomeric compounds, the trans isomers exhibit lambda max at slightly longer wavelength and have larger molar absorptivities than the cis forms. For example, at the two steel beams, the trans isomer shows lambda maximum 294 nanometer and the cis isomer has lambda maximum 278 nanometer. The above observation can be justified in terms of steric hindrance. In the trans isomer, the bulky groups lie on either side of the double bond and there is no steric hindrance. As a result, the ethylene double bond and the pi bonds of benzene ring lie in the same plane and the pi orbital overlap of the conjugated system is quite effective. Therefore, the trans isomer absorbs at longer wavelength. In the cis isomer, the bulky groups lie on the same side of the double bond, giving rise to steric hindrance. Therefore, the ethylene double bond and pi bonds of benzene are forced to be non-planar. Due to this distortion, the pi orbital overlap is not so effective. The decrease in pi orbital overlap leads to decrease in conjugation. Hence, the cis isomer absorbs at shorter wavelength. Detection of functional groups. UV spectrum can be used for the detection of certain functional groups and other structural features if the absorption takes place above 200 nanometer. Even the absence of any absorption above 200 nanometer is of some utility as it shows the absence of conjugation carbonyl group or benzene rings in the compound. Determination of strength of hydrogen bonding. If a compound forms hydrogen bonds with protic solvents such as water and alcohol, it is possible to find the strength of hydrogen bonding by comparing the lambda maximum in the protic solvent with lambda maximum in a non-polar solvent. For example, carbonyl compounds form hydrogen bonds between water and carbonyl oxygen. As a result, the energy of an electrons of carbonyl oxygen in the ground state decreases by an amount equal to the strength of the hydrogen bond. Consequently, the n to pi star transition of the carbonyl compounds requires more energy and therefore it is shifted to lower wavelength. For example, n to pi star transition of acetone in hexane takes place at 279 nanometer, but in water it occurs at 264 nanometer. From the above hyposochromic shift of 15 nanometer, the strength of hydrogen bond between water and acetone can be calculated. Study of keto-enol tautomerism. In case of compounds which exhibit keto-enol tautomerism, UV spectra shows characteristic absorption bands of both the keto and enol forms. For example, ethyl acetoacetate, which exists as an equilibrium mixture of keto and enol tautomers, shows two absorption bands for the keto and enol forms respectively. The keto forms has lambda maximum 275 nanometer with very low intensity 16, while the enol form has lambda maximum 244 nm with high intensity 16,000. Quantitative analysis. UV spectroscopy provides a very sensitive method of quantitative analysis. It is based upon Beer-Lambert's law, which relates the absorbance of a substance with its concentration, path length, and molar absorptivity. That is A is equals to epsilon Cl. For example, we can find the concentration of vitamin A in a sample by determining the absorbance of the given sample. Pure vitamin A has lambda maximum 325 nanometer. If the given sample when taken in a cell with a path length of 1 cm shows an absorbance of 0.75 at 325 nanometer, its concentration can be calculated as follows. Purification control. UV spectroscopy is also used for purification control in dyestuff and ferromacritual industries. These are some examples, and here where our chapter is ended. Thank you.